Let us now discuss the concept of analytic functions, which is a stronger concept of differentiability. We say that a function is analytic in an open set if the derivative of f at set exists in all points of that set. Similarly, we say that a function is analytic in a point if it is analytic in a neighborhood of that point. Let's just take an example of this. The function f of set equal to 1 over set is analytic in all points set different from 0. Since the derivative of f is equal to minus 1 over set square when set is different from 0. So in this case, differentiability and the fact that the function is analytic seems to be the same, or it is the same. Here is an example where the function is not analytic in all points, but it's differentiable in one point. Recall that this function was not differentiable in any point except at the point set equal to 0. But it's not analytic in that point, and the reason why it's not analytic in that point is that it is not analytic in a neighborhood of set equal to 0. So that's the restriction for being analytic, that a function which is analytic in a point must also be differentiable in a neighborhood of that point. And so this is an example where it is differentiable at set equal to 0, but not analytic in that point. So this gives us an example of this fact. And a function being analytic implies that it's differentiable, but not vice versa. Let's now discuss the definition of an entire function. That's just an analytic function which is analytic everywhere in the complex plane. A singular point of a function f is a point where f is not analytic, but f is analytic in at least one point in every neighborhood of that point. Here's an example of a function with a singular point at 0. 0 is that singular point. In this case, the function is analytic in all points except at 0. So then it's trivially satisfied as a singular point. The function f of set equal to the absolute value of set square has no singular points. And the reason for this is that it is the candidate for being a singular point could be any point, but except for set equal to 0. But in any neighborhood or small enough neighborhood of that point, the function has no places where it is analytic. So therefore this function has no singular points. We have the following theorem which we will state. If f is analytic in a domain and the derivative of f of z is equal to 0 in this domain, then f must be constant all over.